I'm Supriya Chakrabarti. I'm a professor in the physics department at UMass Lowell. I also direct a research center called Lowell Center for Space Science and Technology, or LOCUST. We have been developing various technologies for studying things that are in space, whether they are about the atmospheres of planets, or these stars, or the regions between stars, or regions between galaxies. One of the most exciting projects that we're working on, it's called Picture.
I'm Chris Mandillo. I'm a research scientist at UMass Lowell. I work with Supriya on a number of different projects and missions. I've been working here for 3 or 4 years, and I did my dissertation with Supriya on a sounding rocket called Picture. It's a mission to directly image dust and debris and possibly exoplanets around nearby sun-like stars.
Some of that work requires developing optical technology. Some of the other part is computer algorithms that come into play. So all of those have to happen and have to work simultaneously and very precisely.
The technology that we've had to mature over the last 10 years includes systems for stabilizing the image optically. As the payload is sort of jittering around pointing at the star, you need to take that jitter and stabilize it so that the star can be centered perfectly on the coronagraph, which blocks the light from the star.
We've been at this thing for a while to show that we can develop telescopes or spectrographs or some other technologies that will stabilize the image or even selectively turn off the light or dim the light of a star. The goal of Picture is to take image of debris disk, which are like asteroid belts, around a nearby sun-like star called Epsilon Eridani. Project Blue is very similar in terms of its challenges because the region between stars are much dimmer than the stars themselves.
So when we approach a challenge like this, we first need to develop requirements for the mission. So we need to understand exactly what we want to do and then what it would take to do that. And then we do a lot of simulation. We do a lot of modeling. We figure out exactly how precisely we need to be able to move certain parts of the instrument. We need to figure out what kind of measurements we need to make and what the noise in those measurements will be in order to drive these moving parts of the instrument. And then we need to figure out how big our telescope has to be, what kind of observations we need to take in order to achieve the science goals of the mission. Coronagraphs were originally developed to block the light from the sun so that you could see the hot corona around the sun. The sort of first coronagraph was a solar eclipse, when the moon passes in front of the sun. The coronagraphs that we use are an internal instrument that is fed by a telescope that essentially blocks the light from the star. It does this in a very, very precise way to eliminate the starlight to see a planet that's 1 billion times dimmer than it, that is at a very, very small angle. It's very, very close to the star. 2 technologies that we've worked on here are nulling interferometers and the vector vortex coronagraph. 2 completely different types of technology for doing this work.
I'm a graduate student in the physics department. This is my 5th year, and I'm working on Picture C along with Glenn and Chris. The instrument we have is not perfect, so the instrument has its irregularities, surface irregularities. The mirrors themselves have surface irregularities and reflections irregularities. So what we are trying to do is use the deformable mirror to correct those, so we get a perfect as much as possible system. So what we are doing here is we apply these certain patterns on the deformable mirror.
And so inside the dark hole area, that's where you look for planets.
Yes.
So where is the star, and where are you looking for planets in the hemisphere down there?
So right now the star would be right in the middle. It's in the simulation it's blocked out. If there's a bright thing, you will see it in this region. So right now these are just speckles due to the mirror's surfaces. So what we need is, in order to see something, we need the best mirror we can get. So we're trying to make the best mirror we can get using the deformable mirrors.
And you're looking for planets in the dark hole?
Yes.
Okay.
What we're trying to do is make the observations over a period of 2 years. Because if there is a planet that we're looking at, that will move from one frame to another. And all of those have to be done in a very careful and methodical way before we could make a claim that what we're seeing is a planet.
The prospect of finding life on another planet sort of just explodes the idea of what's possible in the galaxy and in the universe. Right now we know of life on one planet and one planet only. If we find it on just one more planet, that means it could be everywhere, and it's probably everywhere.
As Carl Sagan told us, extraordinary claims require extraordinary proofs. This will be one such example of an extraordinary claim.